is captured by mathematical form. But there is a lot of intuition around the way the shape is defined, right? So that is what we had seen, that if somebody were to prescribe these 4 points, then one would assume that the curve that the person had in mind is something that looks like this. Okay, it may be up a bit, lower a bit, but then that's the intent, right? And it turns out that Bezier wanted to provide this as a feature where you sort of nudge the curve to the shape, which is why we call these points, the input from the user, these 4 points, as control points. So that's what is here. And the other thing that I would like you to remember is the similarity of this form, right, with the form of the parametric cubic curve we studied, which also had the same form in some sense, where I had some functions or polynomials in U and some things that the user would prescribe. The notation is slightly off, it's just out of habit, but these are the geometric inputs by the user. It consisted of, if you recall, the 2 endpoints and the 2 derivatives at the 2 endpoints. So these are geometric inputs, and these were nothing but some polynomial functions in U, which we call the basis function, right? Because the input would weigh these basis functions, and the resulting weighted function would be the point on the curve for a given U. The Bezier function also looks the same. I have this geometric input, the PIs from the user, and Bi comma n of U are my basis functions now, and they take a standard form, which is this binomial coefficients, also called the Bernstein polynomial. Now, we then showed that if you look at some specific examples, right, the curve has some very desirable properties, and these are important. As you can see here and also in the previous picture, they always interpolate the first and the last point, right? Even if that was not originally thought of, but that's the behavior we get, right? And it has several other interesting sort of properties, right? The first, of course, that the curve interpolates the first and the last point. It is tangent to the first segment and the last segment of the control polygon. This was a very powerful property that it will always lie within the convex hull, which is why, right, when we had this example, right, I never even drew a curve that looked like this, right? I always drew a curve look like that. I never even drew a curve that looked like that as well, right? So both these are violating this convex hull property, which means that the curve will always lie inside a convex combination, the smallest convex combination of these input points, right? And that's a very powerful property that gives a lot of intuitive, feel to the curve that you would get given a set of points, which is why it is possible for you to set up a control polygon that looks like that and know fully well that the resulting curve that you might get will exactly look like this, right? It may be off a little here, a little there, but by and large, this is what the curve will look like. Why? Because it has to take off from here, tangent to this line, it has to end here, tangent to this line, and it must be inside this convex hull, right? And therefore, you get a lot of predictability on the curve. We also, claimed it, we didn't show it, that the Bernstein's function is variation diminishing. Okay. Now this is essentially to say that the points of inflection in the Bezier curve, where the curvature changes sign, is much less than the wriggles in the control polygon. So for example, here, right, I have this change twice, right? The wriggle, there are 2 wriggles here, and yet my Bezier curve has only one inflection point, which is this change in curvature here, right? So in some sense, we can say that the Bezier curve, because of the property of the Bernstein basis function, is smoothing. It tends to be smoothing the wriggles in the control points. So if I have a lot of control points like this, my resulting Bezier curve could well be, just that. In this case, of course, it may even turn out to be like this. If this goes too much down, yes, then it may take some particular shape, right? So this property we haven't studied. I'll just come back to this once I finish the recap. right? Essentially, the Bezier curve is, provides the user a more intuitive way to define a shape, a given shape, because the objective all along, remember, is that there is a shape in the mind of the user, the designer, and one wants to get a representation, a mathematical representation for that curve. So for example, in this case, if I had 4 control points, as in this situation here, I would get automatically a representation that is this, right? And so the shape is then tweaked by the location of these 4 points, but I automatically get a representation for that once I fix the locations of these points. So that is the goal that we had behind this whole study, that I have arbitrary shaped curves, but I must get a representation for that I can then use in the computer to manipulate, right? And this bit here was to show that one can go from a form that looks like this to get the algebraic form, which is, m times b. That's what we show we can get. We then actually looked at this whole thing in a slightly constructive way, a different way, right? Instead of looking at algebraic expressions, right? What we did was we did a series of constructions, geometric constructions, and all the constructions were the same, namely obtaining a linear interpolant, right? So if I start with, say, 4 points, P0, P1, P2, and P3, and I start finding linear interpolations with successive pairs, right? So P0 and P1 is the first pair, and let's say I evaluate the linear interpolant at u equals 0.5. Okay, so let's say u is 0.5. Right? So the first interpolant is the midway between P0 and P1, second between P1 and P2, and the third between P2 and P3. And I have no more pairs, so I stop. But I recursively do this again, which is with the new sets of points I have got, right? So with this pair, and let me just put a name. I think we did do that in the last class, so I'll repeat the same notation style here, right? So let's label these points as I made a mistake. This should have been P1. Let me just fix this now. This should be P1, 1 and P2, 1. So the notation sort of indicates that the first level of linear interpolation, the 0th point, the first point, and the second point. Now again, I do the same thing. The first pair I have is P01, P11. I find the interpolant at u equals 0.5. I have another pair, P11 and P21. I find that interpolant at 0.5, and those are the 2 points I get. No more pairs, I stop. So I label these with the same convention. This is P02 because of the second level, and P12 because of the second point in the second level. Now I have one pair, and I find the linear interpolant at this, and I label this P03. So all I have done is a series of linear interpolations. Okay. So at the end of this, it turns out that this point P03, right, it turns out is lying on the Bezier curve defined by P0, P1, P2, P3 at u equals 0.5. So what this is saying is that we have a different way to find points on a Bezier curve. Either you can do the algebraic way by evaluating the Bernstein polynomial, with all its concomitant problems of factorials and ratios. But here, all you do is a series of linear interpolations, and you get the point on the curve. And so that seems like a more robust way of doing this. And that's where we have done it here. I suppose the notation is somewhat different because I used this figure from some other source, right? But you can see that the final interpolant lying on the curve, right? And we will be able to generate points for all the other values of u as well, right? So in some sense, I can have a very simple and elegant scheme, which is very robust, because linear interpolation is just the evaluation of the following expression. P of u equals 1 minus u times p. Let me not say P of u. let's see, say Pj of R right is Pj R minus 1 plus U times Pj plus 1 R minus 1. Okay, and I do this for R going from 1, right? How many times do I do this? So this is the first, this is the second, and this is the third. So that is R equals 1 to n. And each time in this, I go for j belonging to 0 to how many times do I do this, right? The first time I have how many interpolations? 3. And second times, do we see that? How many pairs of points do we get each time? That's what we do, right? So the first time I had 1, 2, 3. That's not looking right, is it? J, yeah, this is right. So n minus r would be P2, right, in the first instance, and I get P2 and P3, and then everything else will work. So this is the just a simple algorithm to find points on the Bezier curve. And you can add another loop in U at the outside, which is U goes from 0 to 1. So this is a very elegant scheme, but it is more elegant because it also tells you where the properties come from. Right? So let me just write down the initial set, which is P3, P2, P1, and P0. Right? That's my initial starting point. Let's say I do the first level of interpolations at U equal to 0. Right? So first pair is P0, P1, I get P0. Second pair is P1, P2, I get P1. And third pair is P2, P3, I get P2. Now, again, I do the next one at U equal to 0. I get P0 for the first pair and P1 for the second pair. And the last iteration, I have only one interpolation, that is P0, and that's the point on the Bezier curve for U equal to 0. You can do the same thing for U equals 1 and show that the point is P3. And therefore, this scheme allows you to explain why you get endpoint interpolation with this Bezier formulation. The other interesting point is that this linear interpolation is always a convex combination. And therefore, right, all the points that you get will lie inside the convex hull. So every time you keep taking convex combinations, right, they will maintain this property that they'll be inside the convex combination of the original set of points, which is P0, P1, P2, P3. And that's where the convex hull property comes from. Okay. So that's essentially what the Bezier curve is. And I just need to talk a little bit about this one property that I didn't talk about, which is, or maybe we did. I'll just, I think we did talk about this, right? I showed you that if I have a combination of points, P as a weighted combination of a set of points Pi, right? Where the only additional constraint I have is that the weights add up to 1. Right? We were able to show that a transformation T, right, which involves a rotation or a translation, right? Let's say a rotation and a translation, right, is equivalent to me doing this. Okay. Now, what does this mean? What this means is that I can either take the weighted combination and subject it to a transformation, or I can transform my individual geometric inputs, the points, and then apply the combination, and I will get the same result. Now, why is this important? This is important because for the Bezier curve, right, if you look at the curve, we said this is P of U, equals I to N Pi, which is the same here. But what are the alpha i's? The alpha i's are nothing but this Bernstein polynomial, right? Now, I'm just going to state it now. I'm not going to prove it to you. I'm hoping that you remember your high school algebra, right? So 1 equals 1 power n. That's a truism. That's equal to 1 minus u plus u power n. And this, if you remember your binomial theorem, is nothing but sigma bin comma u. Okay, I'll just expand this. This is your NCI 1 minus u n minus I u power I. Right? And therefore, what this small proof shows is that this condition, that the transformation of the combination is the same as transforming the individual components and then combining, applies for the Bezier curve as well. So I can either transform the curve or I can transform the control points and then generate the curve. Now, why is this a big deal? I mean, just think of a rotation that you do normally on your screen, right? Every time you move your mouse to drag the curve in different orientations, you're subjecting it to some transformation. Now, if you have, say, 10,000 points on the curve to draw, you have to do for each step 10,000 transformations and then, finding the curve corresponding to the new set of, and drawing those 10,000 points every time, right? Instead, all you do is you just have to transform these small n points, which is much smaller than 10,000, and then recompute the curve, which, as we saw, is just a series of linear interpolations somewhere over here. Yeah, as a series of linear, where is it? Yeah, as here, as a series of linear interpolations, again, subject to this small n only, and therefore you can be more efficient in applying these kind of transformations, right? So that's a very powerful utility for you to have. And just to tell you where this might come in handy is that all your fonts, right, that you use are likely represented as curves, either Bezier or some other form, right? Now, if you want to sort of scale or rotate and transform this somehow, right, every time that you want to do this, right, you just need to take the control points corresponding to this and transform them, and then keep generating the transformed font, right? So that makes it very elegant way of doing these things and an efficient way of doing these things as well. Any questions so far before we start on to the topic today? Okay, if there are no questions, then what I will do is I will start the thing today. And that has to do with limitations. So on paper now, we saw that the Bezier curve has these wonderful properties, right? It can be used to define arbitrary shape. And the input required from the user is geometrically very intuitive. They don't have to compute any derivatives or tangents or slopes. They just have to sort of guide the curve by picking points, and by sliding the points up or down, they can get the shape they want. And computation of it is fairly straightforward, and it has all these very nice properties. So the question now to you is that do you see any problems with the Bezier curve? From whatever you have understood so far, do you see any issues with the use of Bezier curve? Or can we stop this conversation right now and say, okay, curves, we are done, Bezier curves, and we can go on to surfaces now? Well, you're thinking, let me just put up a sketch here, right? Typically, right, you may want to design some shape which looks like this, and you may apportion this into 3 tasks and give it to 3 different teams to do this, or 3 different individuals to do this, right? And mainly because there could be some nuances in the interior. So I'll come to that in a minute. But now the person who is doing the middle portion, let's say that they start a little late and these two are already done. Right? So when the person starts this particular curve here, right, what do they inherit? The endpoints are fixed, right? Therefore, they have no choice here, which is not too bad, I would say. So let me call this as P2 naught, and I'll call this as P2 3. Let's assume that these are all cubic curves. Right? So n plus 1 is 4, n is equal to 3. Now, clearly, to get a cubic curve, the designer has the freedom to prescribe 2 more points. Right? You need 4 control points to define the Bezier curve, which is there in the middle. Now, question to you is that how much freedom does the user have in prescribing the next 2 points, the middle 2 points? Meaning, are there any degrees of freedom left for the designer to even define this curve? Any thoughts? Well, would anybody accept if the designer picks these two? Let me just choose a different color so that it looks different now. Would anybody accept if the designer picks these as the new control polygon and this curve goes like this? That would not be acceptable, right? Because there is a desire, right, which is implicit in the way I have drawn this here, that I have some amount of continuity of the derivatives at the 2 ends, namely at P2, 0 and at P3 to 0. Because not only does this have to be equal to P13 and this have to be equal to P30, right? These are the control points on this side and these are the control points on this side. But I also expect the curve to be tangent, continuous, right? Smooth here. Now, if I want that from the properties of the Bezier curve, right? This has some control polygon already defined. Then I have to ensure that the next point lies on this line. Otherwise, my curve will not be tangent to this line. Likewise, here, if this is sorry. Right. So likewise here, this curve is tangent to this line, and therefore the middle curve also has to be tangent to that line, and therefore the other control point has to lie on this. Right. And so at best, I can pick points on these 2 lines and say that that is my control polygon for this curve. So in some sense, there is no degree of freedom left. Now this is not too bad, right? But now supposing the manager who is responsible for this overall project says that I would like to create a small hump here in this, a little detail, right? And the detail could be, a shape that looks like this. What can the user do? How will the designer get that shape in that middle piece, while of course not violating the continuity requirement at the 2 ends? Can the designer do anything? Any thoughts?
So it will get more complex.
No, more complex which way? Where do you think the complexity is coming from?
Like the points, the control points number will increase.
Why would they increase? I mean, why should they increase? Okay, let me ask you this question first.
So we can see there are the number of curves is the continuous curve is the same, but the number of hump as a whole that becomes 1, 2, 3, 4, and 5. Like the middle hump is kind of
Okay.
splitting.
I understood your solution now. I understood your solution. So what you are proposing is that the designer will treat this portion as one curve, this portion as another curve, and this portion as a third curve, and then design the three curves. Is that what you're saying?
Yes, sir.
Good. That is the correct answer. So that is a possibility that instead of trying to, somehow get this hump in a Bezier curve, the designer will sort of split it from, here to here as one curve, here to here as another curve, and the last one as another curve. And while that is a solution, right, and it is a correct solution as well, but you also have said what the problem with that solution is, that you have unnecessarily increased the number of curves that you want to keep, right, that you have to manage, right? You already have 3 segments. Now, just to get this hump, you have added 2 more segments. So you have a total of 5 segments to now track with you for this whole composite curve. Now, that is not a good idea, right? You would like to keep the number of entities that you want to manage as small as possible. So now if the designer, the manager insists that no, 5 is not acceptable, I want you to do it in only 3, right? Then what options do you have?
So,
Yes,
hello?
Go ahead.
So in that case, we can eliminate the P02 and P32 and direct come over to the hump portion. So,
So you are saying that I will go and tamper with the 2 curves that have already been frozen by design. That's what you're saying. Yes or no?
Yes, sir, in some sense.
Okay, so this is one of the realities of real world design is that what is done, you will have to work around that. Very rarely would anybody allow you to give you a clean slate and saying that, oh, it doesn't matter, you can change their design as well and do it. No, once that is proven and is working, nobody will allow you to touch that. Nobody will allow you to touch that. So this is one real problem that people will encounter in real life, right? Especially when different teams. I have given a very sort of academic example, right? But one can find more complex versions of the same example where this task was done in one geographic location, this task was done in another, or maybe this came from an older design, these two came from an older design, and they only want to change this part of it because some user has said that that'll be nice to have a hump here. Okay, it will be driven by only considerations like these. But the point is that once this is frozen and they have tooling for this and maybe other things ready for that, nobody will allow you to touch these 2 parts. Nobody. Okay, you will have to manage here. And so the only way to manage that and also give only one curve to the user, it turns out. So let me just draw, this part here and this part there. And this one, I'll try to get it in a different color again, So now the interest is to get this curve here, right? The only way to do this is to actually start with this design, which is easier because the tangents are known, and I get this. But this will not give me this curve. It will give me some curve that looks like this. Right? Now, remember, we had shown you a picture here, right? That if you moved P2 from here to here, the curve went from here to here. Right? That's local change that was possible. Now, can we do the same thing here? Right? That I have only these 4 points, right? 1, 2, 3, and 4. So can I move any of these points to sort of get this hump, up? Conceivably, I can move this point up in that direction or this point up in that direction, and I can get that, perhaps. Right? That's one way to do this. But what is the implication? Your direction of the tangent will change. So you can't do that. Now, the only way you can do that is by introducing a new control polygon for the same Bezier curve, right? So I'm running out of space to draw. Let me just go onto the side here. If I can go onto the side here.
Sir,
Yeah.
so did the previous the CAD softwares use the Bezier curve or just
Oh,
type
yes.
into display?
No. There is a historical relevance to this. Most popular CAD package, CATIA, was originally written on the basis of Bezier curves. Now, of course, they may also have changed, but this is originally supporting only Bezier curves. Okay, so what is the point I wanted to make? The point I wanted to make was, so I'm just going to draw this curve now, okay, which is a control polygon, which looks like this, slightly exaggerated. And that is my curve, but I want to get some detail here like that. I cannot move this because this line is locked, and I cannot move this because this line is locked. Okay. So I said the only way is to get, I cannot move this point, I cannot move this point. So I now manage or manipulate this curve by defining a new set of control polygon, which will have these points. Okay, so let me call this, I'm going to drop that subscript, but let me see if I can keep it for some more time. P0, 2, I'll say P1, 2, no, yeah, P2, 2 and P3, 2. This was the original curve, which I could not change at all. Now I define a Q0, 2, which is the same as this, but the new Q1, 2 is this, Q2, 2 is this, and Q3, 2 is this, and this is equal to Q4. Okay, so the new control polygon with a different color looks like this. Okay, and now, so if you buy this statement from me that for this new control polygon that I have drawn, right, the Q1, the curve remains the same. Would you have any reason to contest that claim, or do you agree with me? That I can find a set of these points, right, which will give me the same Bezier curve. Does anybody feel that my statement is incorrect and that you cannot find a set of points like this, or this set of points that I have drawn will not give you the same curve? Well, the way to look at this question is the following. You have the shape in front of you, right? So the curve will start at the end point. So the end point is the same, so that is a tick. And likewise here also, it will end at Q4, but it is the same as P3. Therefore, the starting and the ending point of the new curve is the same as the starting and ending point of the last curve, so that is not a problem. Now, the curve will take off tangent to the first polygon leg. Now, the new curve is taking off tangent to Q02, Q22, but that is the same line. And likewise, it ends tangent to the last polygon leg, and that is also the same line. And therefore, the direction of the derivative at the two ends are also identical, and therefore I can tick that also. Right? And the convex hull, it turns out, is almost the same, right? It's not this thing. So therefore, I would expect this curve to be the same. There's nothing, so far that we have seen from the properties of the Bezier curve to tell you that this curve will be any different from the original curve. Okay. That said, there is also a formal proof for this, but we are not going to go into that proof. But I just want to give you some qualitative arguments that I'm not very far off in claiming that these new polygon Q will give me the same curve as the old polygon P. Okay. What is the difference between the two polygons? What do you see is the difference? In one case, so let me write it this formally. P of u originally was this, I equals 0 to 3 P2j B j comma 3 of u. And we are saying that this is exactly identical to I equals 0 to 4 Q j 2 B j comma 4 of u. That's what we are saying. Right? N is 4 in one case, 3 is in previous case. So that's algebraic difference, but qualitatively what has changed now? You had a cubic curve that was cubic to begin with. And now the same curve has a representation whose degree has changed now to quartic. Right? This polynomial, I mean, this curve will have a degree equal to 4, n. And here the degree is 3, which is cubic. But the curve is identical. If I move in the U space from 0 to 1, both will give me the same curve, the gray curve. But what have I achieved with this additional point? Now I can move this point in, right, to get this dip that I want. So if I were to move this point to some location here, right, let me call that Q prime to, then possibly I may be able to get this hump that we were interested in. Right? That's point 1. Point 2 is that you can do this exercise as many number of times. I can define another control polygon where the points are here, 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 and here, which means now I have 6 control points and it defines the same curve. But now I have 3 points that I can move instead of 2, right? Because the tangent is fixed by this, the tangent is fixed by that, but I have an additional 2 points here, 1 and 2 points here, which I can move. You can do it one more time and you can get 3 additional points to move. So what is happening is that with every such, step that I'm doing, I'm increasing the flexibility available to the designer, right? With the green polygon, I have 1 extra point. With the, we have used all colors, is it? Let me see if there is a blue somewhere. Then with this polygon, I have 2 additional points to move, and I can get another one with 3 and 4 and keep going like that. So that is desirable because now I have a way to achieve the goal that we wanted of, introducing a small hump or a dip in this shape. But the price you pay is that every time you get this additional flexibility, your degree has gone up. Okay. So in the other solution that your colleague gave, we increase the number of curve segments itself. Right? Here, the number of curve segments are the same. I have still 3 segments, but one of the segments I am now having a higher degree of the polynomial. And we had seen in the first class that has its own baggage of additional effort in terms of computations and number of roots, etc. And therefore that is not desirable. And so that is one of the limitations of the Bezier curve that we are concerned with. If I can get this. Yeah. So the degree of the curve in the case of the Bezier, because of the Bernstein basis, is always related to the number of control points. Right? So it is always related to the number of control points. which is why you are having the situation that my interest is in increasing the flexibility to the designer, and therefore I'm adding a control point. But what this does is that it increases the degree of the curve. Okay, and so that is the price you pay for having additional flexibility in the curve. Just 1 second. Yeah, sorry about that. So, you know, the flexibility that the designer wants comes at the price of the increased degree of the curve. That's one problem. The other problem, let me go back to this picture here, right? That you have moved 1 point, 1 control point, right? But if you look at the effect on the shape of the curve, right? The curve has changed everywhere in this interval of 0 to 1. Everywhere, right? Except at the two ends, it has changed shape everywhere. So those two are undesirable in some sense, right? That we don't want the flexibility to be linked to the degree, and we would like the change in shape to be localized, right? If you make a small change here in this example, right? The whole shape is changing. Of course, I'm still protecting the tangent, but the shape is changing everywhere. And that is not desirable. I would like to keep the shape change only here, and everywhere else it sort of remains the same. So those are the two problems, that increased flexibility leads to increased degree, and local change in shape is not localized. And therefore, we have to come up with a different form now, which addresses these two problems. And that is a new kind of a curve, which we call the B-spline curve. Okay. So while the Bezier curve is very attractive, we have these two major limitations. And as you can see, this is a very big limitation, that if you cannot allow the designer the flexibility to add local features or local details in the curve or the surface, then you're tying their hands up. And in fact, in response to somebody's question, I had said that CATIA started with the Bezier curve, but their approach was similar to what the colleague had suggested for this problem, that you would have to divide this into 3 Bezier curves. Now, that is a good solution, except there are 2 problems now, right? That every time you will have to maintain continuity at the junctions by hand, right? So if you change this, you have to remember that there is another curve here, and therefore I must make sure that this continuity is maintained, right? And so that's a big problem. But CATIA was doing that, and that's what made it very cumbersome when in the early days with the CAD tool, where one would have to think of the detail one wanted and have curves according to that, and define it only from here to here and have a separate curve for the detail that you want there. All that calls for, enormous amounts of planning and forethought during the design process, which is taking away, from the flexibility that the user needs to have. So that brings us to the B-spline. And again, we start the same way with the B-spline as well, where we look at the form first. And while the algebra is in front of you, our hope is not to focus too much on the algebra and stay on the intuitive side of things. Okay, so let me also say something that I would not expect you to remember these expressions, right? Come exam time, you're free to sort of I can write this on the board for you so that you don't have to remember this expression. Right? But the properties, the behavior, and the intuitive feel for the curve, those are the things that you need to, appreciate and keep about these curves. Okay, the expression itself is not significant at all. We use it only to explain things, but you don't need to remember this. You can always look it up. Okay, fine. So the form here, right, of the spline curve is very similar to what we saw for the Bezier curve as well. Right? In the case of the Bezier, remember the form we had written is I equals 0 n pi bi comma n of u. Right? That's the form. So this was the geometric control points, and these were the basis functions. Right? Just like your xi plus yj plus zk, right? Where x, y, and z are the values, I, j, k are the basis vectors. Here, these are the basis functions, pi's are the points. Here, also the same thing. Pi in this instance are the geometric input from the user, in this case points, and nik of u are the basis functions. Okay, so that's the first point that you should keep in mind, that the form hasn't changed across the Bezier curve or even the parametric cubic curve. Okay, the form is the same. I have some geometric inputs and some basis functions which are polynomials in U. Here also it was a polynomial in U, and we will see what you get here. But if you can look at the expression below, you can immediately guess that it will be a polynomial expression in U. The only difference across all three of them, across here and here, of course, there was a difference in the geometric coefficients also. Here, there were both points and derivatives, whereas here they were all only points, and here also they are only points. PI's are only a set of n plus 1 points. Okay. The basis function is also different. I had a different set of polynomials in U here. I had the Bernstein polynomial here, and here I have a strange looking polynomial. Okay. What is strange about this? Strange about this is that the polynomial is defined recursively. Meaning nik, which is the function of interest to me, happens to be defined in terms of functions ik minus 1. Okay, so it is not a single evaluation. I have to do a series of evaluations to come up to the basis functions that I need. That's one difference. The other interesting difference, of course, is here that the terminating basis function, I1, right? I can't have anything below that. So I start from ni1, then ni2, which is defined in terms of ni1, then ni3, which is defined in terms of ni2, and so forth, right? But this function is defined only over a certain range of u, the parametric variable. So if I have a parametric interval for the curve, which is going from 0 to 1, this basis function ni comma 1 is defined only on some interval. And this following statement is even more important, 0 otherwise. Right? Which means that the function is only defined here as a step, and elsewhere it is 0. Okay. So those are the two big differences. That first, I have the function which is recursively defined, and two, it is not defined everywhere, right? It is defined only over a certain interval of the parametric space. Okay, and as you can see, there are two new parameters that are involved here. One is this parameter k, right, which defines the basis function, right? We don't know what it is right now. We will come to that in a minute. And second are these elements xi plus 1, right? So xi plus 1 first, the definition, and then I will tell you the physical significance of that. These are referred to as the knot elements or the knots, right? And we define a vector of such knots, right? Xi, which is denoted by capital X, right? And this is n plus k plus 1 long vector. Okay, so n relates to the number of points you have input. K we don't know yet, and we will prescribe that in a minute. But this vector is this much long, right? 0 to n plus k. Now, the story is revealed right away, right? What k is, right? K is a parameter now that controls the degree of the curve. And this is something that you should be able to see immediately, right? Why? Because of this recursion that we have defined here, right? So ni1, let's say, is a constant 1, right? Then ni2, when I define, it is defined in terms of ni1 and I plus 1, 1. We'll ignore this for the minute, but you see here that this is multiplied by a term of the type u minus xi, right? So this is u. Now ni3 you will see is ni2, which is of the type u, and it is multiplied by another u from here. Therefore, this becomes u square. And I hope you get the drift now, right? That k in some sense determines the degree of the polynomial, which is always k minus 1, or k is the order of the curve. So right there, the first of the requirement is met now, which is that this number n, which controls the number of control points that you are prescribing, has no say or effect on the degree of the curve, right? Which means that you can have a quadratic curve with k equals 3, but n equals 100, right? And that's a very powerful thing now, because you have so many more control points now to move around and change the shape, add features, details on the shape of the curve without having to worry that the curve will not remain quadratic. It will always remain quadratic. Okay, so just by the choice of the way the basis function is defined, right, you have addressed the first problem, which is the flexibility in terms of the number of control points is no longer linked to the degree of the curve. That's the first point. Now we need to look at this point of local control, and we'll do that in some detail. But first, let's look at what we have now, right? With the spline definition that you see here, right, along with the definition of the basis function, there are 4 parameters now that have to be prescribed before we can even define the curve, right? N. So I need to keep both in screen. Let's see how much I can do. Not much. Okay, doesn't matter. I hope you will remember this. So n is, as we said, is the number of control points related to the number of control points, which happens to be n plus 1, right? So if you prescribe n plus 1 points, n is automatically picked. K, I just showed you by example, right? Not by proof, but by example, that k relates to the order of the curve. The degree is k minus 1, right? The other parameter that you need to provide is pi, the n plus 1 control points, right? And in addition, we also have to prescribe the so-called not vector, right? This n plus k plus 1 elements not vector. Okay, so the first thing that I will do is to tell you what the not vector can be, right? So we said that this is xi, and there are only 2 conditions on this, that I belongs to 0 to n plus k, meaning there are n plus k plus 1 elements in this vector, and 2, it is a non-decreasing vector. Those are the only 2 conditions. Okay, which means if you were to take a quadratic curve, so k equals 3, and let's say you wanted 6 control points, so n is equal to 5, then your x basically will have the following elements, x0 all the way till x8. So 9 elements, right? N plus k plus 1. Now this can be something as simple as 1, 2, all the way till what should it be? All right, okay, let me say 0. 1 all the way till 8. So that's one knot vector because it satisfies both these conditions. There are 9 elements and it's monotonically increasing, right? It can also be something like this, right? 0, 0, 0, 1, 2, 3, 4, 4, 4. This is also an acceptable knot vector. Why? Again, there are 9 elements. That is clear, right? First condition is satisfied and it is non-decreasing, right? It is equal, but it is not decreasing. Therefore, that's again satisfied. And you can also have, some very strange elements as well. 0, 1.1, 5.3, 7.674, and so forth, till 9 elements. So all of these are acceptable knot vectors. So clearly that means that this is a choice that we must exercise. Okay. So let me just go to the next. Oh, there is a blank slide, means I'm in trouble, but let me just put this up and then stop here. Right? The reason I put this figure up is that this is a situation. How many points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So n is equal to 9. Okay. Now, the fact that it has ended like this, right? This is one type of a knot vector. This is another type of a knot vector. So n and k are the same everywhere here. Okay. N and k are the same. And here as well. So n is 9 and maybe k is equal to 4, sorry. So degree cubic is the curve, right? But what has changed across these 3 pictures is that x here, right, is the first variety that I wrote, which is 0, 1, 2, all the way till 13. So if I use this knot vector of 0, 1, 2, all the way till 13, I get something like this, right? This, I will tell you what the knot vector corresponding to this is. It is slightly different. This is, of course, to show that I can get closed knot vector, closed curves also with the same formalism, except by the fact that I have repeated the last control point to be the same as the first control point. Right? So if I started, I don't know where the 0 is, probably the 0 is here. So I add one more point, endpoint here, and that becomes my last point. Okay. Actually, looks like the last point should be somewhere over here, because that's when it will be tangent to the first and the last segment, right? So this is the last and the first segment here, 0, 1 or 8, 0, whichever way it is. Right? So these two show the power of the choice of x, right? In one case, I have forced it to sort of go to the first and the last point. In another case, it sort of hangs somewhere in between, but it is still nevertheless a smooth curve. So now we will see what the choice of x that we will use, and then derive some of the other things that you need to know about the spline curve. I will stop here. If you have any quick questions, please ask them now. Otherwise, I will recap this again on Monday, and then you can ask more questions. So any quick questions now? Okay, if there are no questions, then I will stop here. I will put these slides up to today's lecture in this Teams file section. You should be able to get these slides there now. And we will meet on Monday for continuing the same topic again. Okay, thank you very much. Yeah.
Thank you, sir.
Thank you, sir. Thank you. Yeah.